Hello, everyone. My name is Rishabh Subramanya. I am a sophomore at the Energy Institute High School in Houston, Texas, advised by Mr. Lyle Regenvetter at the Decode Lab in MIT. Today, I'll be presenting on a data-driven machine learning approach to the structural optimization of quadcopters. So, what is data-driven design exactly? Data-driven design or engineering is an emerging field of design technology wherein data points find optimal designs as opposed to a human designer. The benefit of such a method is that humans cannot take every factor of design optimization into consideration, whereas automated technology can. Data-driven design is used in fields such as microfluidics, airflow design, vehicle optimization, etc. But why quadcopters? As all of you know, quadcopters are ubiquitous, extremely prevalent, and pervade into many aspects of the global economy. As a result, in the past few decades, quadcopters have been heavily used and researched on in the healthcare, disaster response, and military reconnaissance sectors, to name just a few. Thus, research into quadcopter design and structural performance is exceedingly necessary. Lastly, quadcopters are a prime example of products that have diversity and variation in design, but have similar design objectives in their respective use cases. So what are the overarching goals of this project specifically? Firstly, using thousands of different data points, we want to find and learn what the optimal quadcopter designs are. This is based on each design's performance under stresses. Secondly, using existing machine learning frameworks, existing quadcopter designs can be altered and thus optimized in an automated fashion. This is based off the existing framework in the previous step. The first step in our methodology is parameterization, the process of determining the common features amongst nearly all existing quadcopter designs. This allows for quadcopter design to be generalized, thus helping to create the dataset. For quadcopters, parameters include quantities such as length, width, thickness, and material. After the parameters are determined, these are implemented when creating the initial model geometry. Finite element analysis, or FEA, shows how objects react to real-world forces, tensions, and stresses, and thus is key in determining structural results. Based on previous literature and available specifications, we can determine that loads such as vertical and horizontal bending and centrifugal tension are the most significant forces that quadcopters encounter. Aerodynamic forces such as drag are negligible in this case. In order to do this, an FEA study needs to be created by determining mesh resolution in the planes on which the loads are applied. For this study, the in-plane and normal planes are selected, as shown. To determine our initial models, the material is an extremely important parameter when considering the structural reaction of quadcopters. As a result, our methodology incorporates 12 different classes of predefined materials such as steel, aluminum, zinc, and carbon alloys, some of which are shown here. The result of this is 12 different base models upon which a dataset can be built upon. One of the biggest ways our methodology differentiates itself from existing literature is application of the Sobel sequence. Let me first give you an example. This graph is composed of randomly generated values between the ranges. However, there are several regions where there is either a high concentration of points or a relatively low concentration. This is a relatively inaccurate representation of all possible points within the region. The application of a Sobel sequence, however, allows for random points to be generated in a more distributed pattern that accurately represents the points within the region. Thus, regular randomness is transformed into distributed randomness. The result, the Sobel methodology results in a more accurate representation of available data points and ranges. But how does this apply to this methodology? Each numerical vector or point on a Sobel sequence generated graph is a quadcopter design. For example, let's say we have arm length on the x-axis and shell thickness on the y-axis, and we want to sample random drone designs. We expand this concept to a 9-dimensional space and sample points from this 9D space. Even if our Sobel sequence generates thousands of different data points, how can engineers determine if it is good? We want a quantifiable metric other than physical appearance, so we use sensor values. Each FEA study produced will give us sensors like weight, von Mises stress, resultant displacement, and factor of safety. These sensors become extremely important when we are training our regression model, which I'll describe later on. An equally important question arises. Yes, we can generate thousands of models, but how many models are feasible? Meaning, how many of them can be effectively manufactured? From the 22,000 generated models, less than 15% are geometrically feasible, meaning software cannot properly generate models and thus cannot be manufactured. As a result, our framework must introduce infeasibility checks using geometric calculations in order to eliminate infeasible models, thus increasing the percentage of feasible models. A sample of the infeasible models and feasible models are shown. As shown, infeasible models are missing key geometry. However, even amongst the feasible models, there are some obvious errors, such as the top of the arm sticking out of the top of the drone body. Thus, Questions we must consider in order to determine our feasibility checks include: what breaks the model? What happens when we change certain parameters, and how does that affect model generation? Another question we must ask is why a significant percentage of infeasible models suffer from invalid geometry. For example, one straightforward check is that the thickness of the shell of the arm must be less than the thickness of the arm. Such calculation eliminates around 60% of Sobel models directly during the Sobel sequence generation period, which is a good thing. However, despite our best efforts, modeling software is the ultimate determinant in model generation. Regardless, we can look at the sensors that the model outputs and determine whether they are practical. The result? Only about 25% of models that the software ran were determined infeasible. This is a significant increase in feasibility percentage, as the percentage has increased from 15% to 75% of models that are run through the design study successfully. Again, a sample of infeasible and feasible models that were run are shown. These models are much more geometrically feasible and are one step closer to being effectively manufactured. However, although these infeasible models look externally adequate, internal geometry errors prevent the model from being functionally generated. So let's take a step back and see what the process is up till this point. From a parameterization step, we generate 12 models. From these models, the Sobel sequence generates 22,000 models. Then geometric calculations result in 7,000 models. From there, after putting it through the design study, it results in approximately 5,300 viable data points. Now that we have our data-driven points, we can fit them into a standard regression model. We fit our features, or x values, for prediction, or y values. We divide our data into predicting and training x and y data. We predict our y data from a set of x data, thus creating the model. We train and tune this using validation data, which will help us determine if the model is regressing correctly. Finally, we test this model using new data and see how the model fares. In this case, our x values are the parameters such as width, and y values are sensors such as stress. The final step is the counterfactual method, a cause and effect relationship. Factual thinking requires that cause determines the effect. However, counterfactual thinking requires that knowing the effect and seeing how changes in the cause results in the desired effect. A great example by data science Christopher Molnar is as follows. If a person applies for a bank loan and gets rejected, we need to consider why they got rejected. What is the smallest change in the cause, example, income, number of credit cards, etc., that will change the application from rejected to approved? In machine learning, this can be described as having predefined y values and seeing if we can find the smallest change in x values to get that predefined y value. For our model, this is groundbreaking. If we know the optimal sensor values from our regression model defined previously, the counterfactual model can actually recommend changes to our x values, our parameters, to optimize a model. Since parameters define model geometry, our model can actually recommend actionable changes to the model geometry. As a result of this innovative framework that we have created here, we can expand this project to more complex and thus more applicable drone designs, eventually reaching a level where our manufactured drones designs can be used for many of the use cases I described previously in our presentation. The framework we have created here can be used in thousands of different applications, from undersea to aviation technology, consumer products to industrial machinery, and structural to aerodynamic optimization. Automated design has the ability to use the power of technology to make the world a safer place. Thank you for listening. I hope you enjoyed this presentation.